Yay! We're starting proofs. This is going to be a lifelong love-hate relationship, but proofs are so important, and I made the mistake of saying to the internet that proofs weren't important, and I was told that is not true at all. So here we are, teaching you proofs. You're welcome, Reddit. So algebraic proofs, we're going to start. So here's the deal. Proofs, what we're going to do is we're going to use logic to prove something without a shadow of a doubt. That's what proofs do. They go through step by step and they say, this is my next step, this is my next step, this is my next step, and it's painful and it's slow and it's okay if that's frustrating for you. But what you're going to find is that we're going to end up pretty soon at the end of October in triangle proofs, which is angle, like if two angles and this side in between them are the same in a different triangle and those two triangles are the same all the way around, that kind of thing. So what we're going to end up doing is we're going to have a bunch of different things that are justifications for a step. Right now, what we have is this. So I went through and I just started out with a couple of proofs cards. In physical class, what I did was I copied these on colors and then we put them in little pockets in our notebooks. But I actually kind of like this better. Watch. Oh, wait, hold on. There was a little bar here. So watch. So I'm going to go to algebra because that's what we're doing right now is we're doing algebraic proofs. And here are the 10 proof cards that we could use in an algebraic proof. It's a non-exhaustive list. Doesn't mean that these are the only things you can use, but I did do my best to find all the ones that we're going to be using. So if I wanted to use the addition property of equality, I can add the same number to both sides of an equation. Here's an example of a proof. If I have a statement that's 5x minus 3 that's been given to me as a starting point, then if I add the 3 to the other side, I get 13. That's the addition property of equality. Just to keep showing you around here, if you press this pink button again, it'll take you back to the main ones. You can go to a different one, or you can press home and go to a different proof card section. Now, like angles, we're not there yet, so it's not filled in, but we are starting with some things that are other. For instance, given. If it's given, it's stated either here or in the picture. And there's definitions sometimes. We're not quite going to get there, but if you do the challenge problem, you will need this. That's why I put it in here already. So I did the definition of congruent segments, say that if two segments are congruent, then they are equal in length. And that's just how that works. So we're going to be using that today. So I'm going to leave it down there. But we're going to talk about algebraic proofs specifically. And you're going to go, what? We're in geometry. Why are we doing algebra again? And the reason we're doing algebra again is because it helps if you do a hard problem using something you already know, right? That's one of actually the tools of problem solving is using a problem that you already know or something simpler. So we're going to use your base knowledge of algebra to practice this stuff before we get into the geometry version of it. So you already know algebra, we're going to teach you proofs. And then you already know proofs, we're going to teach you some geometry with proofs. That's what's going to happen. I hope that you're okay with that. First of all, let's talk about what a proof is. Your book says that a proof is a logical argument that uses deductive reasoning to prove a statement is true. There are different forms of proofs, and there's also different ways to do it. You could also do a proof to do like an inductive reasoning, but we're going to use deductive reasoning. There's different forms of proofs. The one we're going to be using is called a two-column proof. And it looks like this. I never put a line on my J's. On the left side is a statement. So that's saying this is a math problem, or this is an expression, or this is an equation, or this is just sort of a math statement. And then the other side is justification, or a lot of times people will say reason. I personally prefer justification, but your book uses reason a lot, so I'm probably going to alternate back and forth between those two. And so what we have here is we have some sort of statement. The first one will always say given. I'm going to just give you that. It'll always say given because it's going to be given to you. We have to start somewhere. We have to start with some sort of base. And then you'll have a different statement. And then you'll have a reason for it. And then you'll have a different statement and you'll have a reason for it. And then eventually you'll get to whatever you're trying to prove. That was a weird R. It's fine. Because a proof will have the word given and then prove underneath it. So this is a typical 2-column proof. There's also flowchart proofs and paragraph proofs, but we are going to stick with a 2-column proof because it's A, the most common, and B, the other ones are kind of hard to draw. And paragraph proofs are just you writing a bunch of things, and that's hard to follow. So 2-column proofs are easiest to follow and also makes the most sense, to be honest. And so you have statements, you have justification for those statements. Now, this justification is how you got from statement 1 to statement 2. Do I have to write this without the thing? I should just pause it. That's fine. And so on and so forth. So the second justification is from 1 to 2. The third justification is from 2 to 3. Fourth one is from 3 to 4, etc. 2-column proofs could be pages and pages and pages long. Luckily, I'm not going to do that to you. We're going to do a couple of examples in terms of algebra, but this is what proofs are all together. So here's an algebraic proof. All right, here's an algebraic proof. I already said that, sorry. Given this statement, prove x equals 8. And I have to just double check. No, that's not right. 9. I just did that in my head, which is the problem. Train. All right. So we're going to set up our 2-column proof. We're going to write our statement. I'm going to try to do a second one. I'll do a second one below it. That's fine. So we do a statement. I know that I'm going to have to write the original equation, add 5, divide by 2, write the answer. So it'll probably take that many lines, but I'll go to here just in case. It's fine. Justification. Now here's the good news. In most of the following assignments, like after this part, I'm going to give you most of the proof already filled in. We're just going to be practicing using algebra again because it's something that's familiar. Okay, so my first statement is what I have to start with the original problem. Okay, and the justification for this is that it was given to me. It's already provided. This is where I'm starting from. Now, you don't have to show the little plus 5, but what am I doing? I'm adding 5 to both sides, so I get 2x equals 18. I added something to both sides. Let me check my proof cards to see which one of those matches. Oh, look, addition property. I added to both sides. Let me just double check. You can add the same number to each side of an equation. We're good. I added 5 to both sides. So what I write over here is the addition property of equality. Do I have to write property of equality every single time I use this? No. I could write POE instead, and I will for the next one. Property of equality is so common and such a long freaking word that we shorten the heck out of it. Okay, what do I do next when I do this math? Well, next, I'm going to divide both sides by 2, and I'm going to get x equals 9. Let's go back to the algebra cards and see which one of these kind of sounds like that. Division. I divided both sides. Let me check. You can divide both sides of an equation by the same number. Cool. So I divided both sides by 2, so I can use the division property of equality. See how I didn't write the whole thing? We're shortening it. All right. And then, oh, I didn't even put this on the first one. And then once we're done, we're going to do a little box at the bottom. This box at the bottom has a lot of different names, but it's called a tombstone for the most part. And it just showed that the proof is dead. You did it. I know you want to like check off the box and stuff. That's actually not how it works. But if you go look at a magazine, if you have like a physical copy of a magazine, every time an article is done, it'll have a little box. Usually they fill it in, I don't know, aesthetics. But that just means that the article is done. It's a tombstone. They took it from math. We didn't take it from them. Articles took it from us. You also could write the letters Q, E, D when you're done. QED stands for Quod erat demonstrandum, which is Latin for I did it. It's actually Latin for it was to be proven. but I did it better. So you could write the box or QED. I'm going to put a box in this one. I did it. I'm done. That's a lot of information, so let's do another problem. All right, let's do this one. Hold up. Where's my mouse? There it is. Let's try this one. I think I said that already too. All right, we're going to do statements and justifications. This might take the whole page. It might take longer than the whole page, but I don't think so. All right. So I'm going to start with my problem. So I'm going to start with my given statement. So it's given to me that 4 equals negative 10x plus 6 times 2 minus x. That was given to me to start with. That was my first thing I did. So what I'm going to do now is I'm going to probably distribute this 6. So I'm going to distribute the 6 and I'll get 4 equals negative 10x. If I distribute the 6, that's a 12. If I distribute the 6, it'll be minus 6x. Let's go see what property that could be. Maybe distributive property. I can distribute a number into a set of parentheses by multiplying everything inside by that external number. That looks like what I just did. So that's the distributive property. It's not the distributive POE because it's not a property of equality. Because a property of equality specifically goes across an equal sign. And this one's just on one side of the equal sign. So it's just a distributive property. All right. Next, I'm going to maybe collect like terms. Put these two together. So I get 4 equals negative 16x plus 12. I collected like terms. Let's go back to the algebra cards. Collect like terms is not one of them. What's maybe another word for collect like terms? It looks like I simplified. Let's try that. Hey, I can combine like terms. Perfect. So I combined like terms, so I just simplify. Perfect. Okay, now I'm going to move the 12 to be with the 4. So I'm going to subtract the 12. I get negative 8 equals negative 16x. And we already know that one. That's not division. Hold on. That's subtraction property of equality. We actually haven't done that one, but it's the same. It's like addition but subtraction, you know. All right, and then last I'm going to divide by 2, second to last. I get 1/2 equals x. I did the division property of equality. Now here's where you're going to hate me. I'm technically not done because it says that I need to prove that x equals 1/2, and what I actually proved was that 1/2 equals x. I know, don't get mad at me. All right, so there are these 3 extra properties that don't make sense yet because we've done it like addition is addition. Distribution is distribution. That was a weird way to say it. Reflexive, symmetric, and transitive are all 3 brand new properties. So let's look at them. Reflexive property says that everything's equal to itself. And the example down here is that zy equals zy. This would be the case if it said like 1/2 equals 1/2, but it doesn't say that. So let's go back and see what the other ones say. Symmetric property of equality says that I can switch expressions on either side of the equal sign without changing the problem. It's that one. Because what I can do is I can swap these using the symmetric property of equality. All right, let's just check the last one so I can tell you about it. Transitive. Transitive property says that if 2 values are equal to a third value, then they're equal to each other. So in this case, if it would say like 1/2 equals x and x equals y, then I could say that 1/2 equals y. Something like that. That's the transitive property. It's kind of hard to see the reflexive and transitive properties in a proof, but they will exist later, and so I kind of want you to get used to them. So a couple of the problems are just you identifying if it's which property it is. That's all. I forgot one thing. I need to put the little tombstone, or the QED. Quod erat demonstrandum. I did it. You could technically put like a happy face or whatever, but that's not good geometry. So let's stick with either a box or QED to show that you're done. Your homework tonight is going to use words like solve, blank, and justify each step. What it's saying is that it's given this, prove that x equals whatever it equals. So you're going to do this to it, okay? What that means is that I actually have to do this because your book didn't like your book asks you to just like write out each step, but I want you to do it in a two-column proof. That way you get used to the idea of a two-column proof before we get to the fun stuff, which is called geometry. All right. If you want me to do any more problems, please email me. I totally will. I'll do these all day long. We also are going to do some of these in class. So maybe you'll even get it ahead of time. I don't know. I don't know what schedule you're on. But I hope this helped, and I hope it wasn't too long. I'm so sorry if it was. Oof. And I'll see you next time. Bye.